This question involving Hooke's law seemed to cause a few problems, particularly in the parts C and D. So let's have a look at this. So I've started off by drawing a diagram for the first situation, where we've got our particle attached and string. We've got modulus of elasticity, so lambda, and it's attached to the ceiling and it's hanging like that. It's in equilibrium. So I've set my diagram up where we know the natural length is A and I've called the extension X. And in part A, we've just got to show that the distance, so they want the total distance from the ceiling when it's in equilibrium, is 4/3 A. Okay, so if it's in equilibrium, then there's overall no resultant force as it's hanging, which means that the tension has got to be equal to the weight as it's in equilibrium. Okay, so we know using Hooke's law, tension is lambda x over L. So tension is 3 mgx and the natural length is A. That's going to be equal to mg. We can see we can cancel out the mg's. We can rearrange, we get x is A over 3. See, that was extension. So the total distance is going to be A plus 1/3 A, which is 4/3 A as required. Okay. In part B now, we've changed the situation slightly. We've got our particle, but now it's held at a point A where the total distance is 2A, which means we've got the natural length of A and an extension of A now. Okay, so we want to find the acceleration immediately after it's released from rest. So this time there's acceleration, so force is mass times acceleration. So we're going to have the tension, take away the weight because it's going to move upwards as it's now been stretched, it's going to move up, is going to be mass times acceleration. So tension again using Hooke's law, lambda, extension is A, and natural length is A, minus the weight is ma. Do a little bit of cancelling, you can get that the acceleration is 2g. Now, part C was found to be a little bit more difficult, so we want to find the maximum speed as it moves from A to B. Now, at maximum speed, if you think about a velocity time graph, a maximum speed is when the acceleration is 0, because that would be when the gradient of the graph is 0. Now, when the acceleration is 0, that means the resultant force, in this case in the vertical direction, is going to be 0 overall, which means we are at the equilibrium point. Okay, so we can then solve this using energy. So let's have a look. So we've got point A, which is our start, and we've got the equilibrium point, which is going to be our finish. So what types of energy have we got? We've got kinetic energy, gravitational potential energy, and elastic potential energy. So the kinetic energy at A is 0, it hasn't actually got going yet. The gravitational potential energy I'm going to set to be 0, and the elastic potential energy, so elastic potential energy is lambda x squared over 2L, so lambda, our extension is A over 2A was the natural length. When it's at the equilibrium point, it's now got kinetic energy half mv squared. Gravitational potential energy. Now, if you remember from the first part, we showed that the distance, remember we had distance d, right? And we showed that d was 4/3 A. So that means in order to go from point A up to the equilibrium point, the distance is going to be 2/3 a, because it's we've got current length 2a, and it's going to the point where it's 4/3 a. Hopefully that makes sense. So that bit there is going to be 2/3 a. So our gravitational potential energy is mg. H is 2/3 a. And then the thing that a lot of people forgot, and you lose loads of marks if you forget this, is in the equilibrium position, you do still have tension in the string. A lot of people thought the maximum acceleration was when the tension is 0, but it's not. So in equilibrium, we still got some tensions. There's still elastic potential energy. So lambda, remember the extension was 1/3 a, so 1/3 a squared over natural length. Okay, so we can now take all our types of energy, and so what should happen is all the elastic potential energy at the start some of it will be converted kinetic, some gravitational, and some of it will be left as elastic potential. So we've got that equals our types of energy at the end. Okay, and then all we've got to do is solve for all of this. So there's quite a lot of things which will end up cancelling out, but you should be able to rearrange this to get to and then if you simplify all that further, you can get to V equals 4GA over 3, and that's the maximum speed. Okay, so in part D, we're now going to find distance OB. So reading the information, B is the point at which it becomes to instantaneous rest. We can again do this by thinking about energy. So A and B. So what's going to happen here? So we've got all our types again. Well, at the start it had 0 speed, at the end it had 0 speed, so kinetic energy is out of the equation. At the start we're going to set gravitational potential energy to be 0, so at the end mgh, h is actually the distance we're trying to find, because we want to eventually know the distance from O to B. And then elastic potential energy, so we've got elastic potential energy when we start. So we can just copy from part C. And now this is the point where the tension is 0, string is slack. Because this is the point at which there's no more upwards force, so the particle stops and you've just got the weight pulling it back down. At this point, there is no elastic potential energy at point B. That's quite easy then, because we've got all the elastic potential energy is going to be converted to gravitational potential energy, and doing a bit of simplifying, we've got our elastic potential energy equals our gravitational potential energy. So you can get that H is 3 over 2A, but be careful because that wasn't the answer to our question. We've got point A and point B up here, because we've worked out this distance and we wanted the distance O to B. So O to B is going to be 2A, because remember that was the distance to A, minus 3 over 2A. So it's actually going to be a half A.